a lot of functions that we look at are actually some form of composite function. So let's take a look at the idea of continuity in composite functions. So if g is continuous at c, where obviously g is some function, and f is a continuous at g of c, then the composite function f of g of c is also continuous at x equals c. This is saying the limit as x approaches c of f of g of x is equal to f of g of c, or the limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x. So these are saying the same thing. So this probably will make this a little bit more sense when we jump into this and work out just a couple of examples. So let's take a look at this. This is not a composite function. This is actually a sum or summary differences of two functions. This is a polynomial. Cosine is continuous everywhere. So I have a polynomial plus cosine. Both are continuous everywhere. So this is continuous on negative infinity to infinity. Now let's take a look at this one. The numerator here, this is a rational function of, well, not quite by definition because that's not a polynomial, but we tend to treat it, the techniques with a rational function are identical. So this is a polynomial. This is a sine function that's continuous everywhere. So right away I want to say, gosh, it's continuous everywhere, but it's not. It's continuous everywhere that sine x is non-zero. Okay, so this is continuous for all x such that sine of x is not equal to 0. That means x cannot be equal to 0, pi, 2 pi, and so forth. But it's continuous every place else. Now, let f of x equals 2x squared, g of x equals cosine of x, and I want to consider the composite function f of g of x. Well, first of all, f of g of x is going to be 2, well, let me write that. F of g of x equals 2 times, where there used to be an x, I'm putting in g of x, which is cosine. So that's going to be 2 times cosine of x squared. Now, this is continuous everywhere. F is continuous everywhere because it's a polynomial. G of x is continuous everywhere is cosine. Remember, cosine and sine are continuous everywhere. So, because of that, I'm going to say, therefore, f of g of x is continuous everywhere. See, cosine will never be a number that 2x squared can't handle. And because I don't have a fraction, I don't have cosine in the denominator or 2x in the denominator, I don't have to worry about if one of them is 0. All right, so if cosine is 0, who cares? Is this 2 times 0 at 0? That is no big deal. So this composite function is in fact continuous everywhere. Now here's a rational function. Using our notation, even though I call this whole thing f of x, this would be f and this would be g, using our prior notation, but it doesn't really matter. We can call it h and k. That makes no difference. Both these are polynomials. Both of these are continuous everywhere. However, I have to be concerned about when is this equal to 0. Because if this can be equal to 0, I'm going to have an issue here, because that's going to give me some point of discontinuity, either a point or an infinite discontinuity. So x plus 2 equals 0. I don't need that. That implies that x equals negative 2. So I'm going to say that x squared minus 4 over x plus 2 is continuous for all x not equal to negative 2. Now if I take this and do a little algebra on it, I'll see that this is x minus 2 over x plus 2. And this is x plus 2. These cancel out, and I get x minus 2. So this function looks just like x minus 2 everywhere except when x is equal to negative 2. At that point, it's discontinuous. So I know that I actually have a point of discontinuity, because whenever I factor out a rational function, and any factors in the denominator that would create a 0 in the denominator, if that's canceled out, that will give me a whole. So what about this one? We actually talked about this one in an earlier example. See, this is a composite function. If I think of this as g of x equals the square root of x, and h of x equals 9 minus x squared, then that would imply that f of x is actually equal to g composed of h of x. Now, the issue here is the square root of x, g of x, has a limited domain. The domain for g is that x has to be greater than or equal to 0. X would be non-negative. That means this has to be non-negative. So 9 minus x squared has to be greater than or equal to 0, which implies 9 is greater than or equal to x squared, which then implies that square root, both sides, plus or minus 3 has to be greater than or equal to x. Now this is some screwy notation. This will kind of mess you up when you think about trying to interpret this. So really what I want to do is go back to the idea of absolute values and distances. So really what this is telling you is that I have to reside on negative 3 to 3. And taking a square root on both sides of an inequality can get confusing. So we need to keep in mind just exactly what it is that we're trying to accomplish here. And we can quickly see here that if I take the square root of both sides, what I really have, this by definition, is the absolute value of x. In which case I'm really only looking at the positive root. Positive 3. So absolute value of x has to be less than or equal to 3, which is exactly what this is saying right there. I realize that can seem a little bit confusing working with these inequalities and taking square roots and dealing with absolute values. So you may want to go back over this a couple times to catch it. But what this is saying is that this function, this composite function, is continuous on this interval. Outside that interval, g of x is undefined. So if g of x is undefined, that's the square root, then f of x, the composite, must also be undefined. This next example is very similar to that. Again, I can say g of x equals the square root of x. Only this time my h of x, rather than 9 minus x squared, h of x is going to be x squared minus 9. Well, this has to be greater than or equal to 0. So what I need is x squared minus 9 must be greater than or equal to 0 for this to be defined. That implies that x squared has to be greater than or equal to 9. If I take the square root, that by definition, once again, is absolute value of x. So absolute value of x must be greater than or equal to 3. That gives me the interval negative infinity to negative 3, and 3 to infinity. Now let's jump to Maple real quick, and let's just get a quick look at both of these functions to see what they look like. Because this should look like, we did it before, we're going to draw it real quick. This should look like this, where this is -3 and this is 3. But what does this look like? If you start plotting points, you can figure it out, or just put it in your calculator. But let's take a look at Maple. So what I'm going to do is I am going to plot square root of, what was that first one? 9 minus x squared. Let's just go -10 to 10, y equals -10 to 10. This is your basic box. It's really nice and easy to start with, and I can modify it later. Oh, I'm going to jump in here right away and make thickness equal to 3. And boy, I didn't like something there. Oh, I missed my x. I forgot to tell it that x is what goes there. There we go. And there's that little half circle. Now, obviously, if I modify this, maybe -5 to 5, and y -1 to, I don't know, 5. It will help me zoom in a little bit and get a little bit better picture. And then notice just a quick thing on Maple. You notice how this looks kind of lopsided, kind of weird. If I right click on it and I select scaled constrained, it's going to make the x and y axes equal to each other in terms of these distances. One is actually 1. And actually what I see, there's a half circle. Now that other function was simply x squared minus 9. And I'm going to go back to, let's just do 15. Everything should be okay. Oops, what did I mess up here? Oops, I did not get my 9. There we go. Now you can see what's happening. Let's take this y and take y out to 15. And that's what that function is looking like. You can see here in the middle where we said it was undefined, it really is. There's nothing here. Make it quick a little bit bigger for you. That's what the function looks like.